Hello everyone. My name is Hairinand Yevi and I'm from the first MSc of Department of Information Technology, Kannur University, Mangaduvanga. I'm here to talk about my seminar on the topic using inference rules to produce predictable calculus expressions. It is a rule-based approach to mathematical reasoning. This presentation explores how concepts from mathematical logic, specifically inference rules, can be applied to calculus in order to make problem solving more structured, predictable, and systematic. Let us begin by understanding the basic idea behind this approach. We know that mathematics is built on rules and logical reasoning. Every step we perform in solving a problem follows a defined rule. In calculus, we deal with derivatives and integrals, where expressions are transformed step by step using standard formulas. Now, this leads to a central question. Can we treat these calculus transformations like inference rules in logic? That means, can each step be seen as a formal rule? Can we make the process predictable and verifiable? The mathematical logic provides formal systems of reasoning where conclusions are derived using rules. Similarly, calculus studies continuous changes, but the transformations also follow strict rules. So the idea is to connect these two domains. Let us first understand what an inference rules are. So what are inference rules? Inference rules are logical steps used to derive conclusions from known facts or premises. A classic example is mode exponents. If P implies Q and P is true, then Q must also be true. This ensures that reasoning is structured, valid, and predictable. Inference rules are important because they prevent logical errors, they ensure correctness, and they form the foundation of proof systems. So the key idea here is inference rules transform non-truths into new truths in a systematic way. This same concept can be applied in mathematics. Inference rules in mathematics. Here we are going to see how mathematics already use rule-based based transformations. For example, in algebra, we have x plus 0 equal to x. We apply the identity rule. This simplifies the expression without changing its value. Whereas in calculus, if we see x raised to n, we apply the power rule, so the result becomes n into x raised to n minus 1. In equation solving, we balance both sides using valid operations. Each step follows a rule. So clearly, mathematics already behaves like a rule-based system. Each step can be seen as input and then apply rule and then that gives the output. This exactly works how inference rule works in logic. Calculus as a rule-based system. Now let's focus on specifically on calculus. Differentiation is based on a fixed set of rules. Whenever we see a certain type of expression, we apply the corresponding rule. For example, power rule. This reduces exponents and multiply by original power. And sum rule. Differentiate each term separately. And product rule combines derivatives of two functions. The important point is each rule always produces a predictable result. So just like inference rules transform logical statements, calculus rules transform mathematical expressions. This makes calculus a structured and rule-driven system. Chain rule as inference. Now let's check at a more advanced concept, the chain rule. The chain rule is used for composite functions where one function is inside another. This is similar to multi-step inference in logic where one conclusion becomes the input for the next step. Here's how it works. First, we identify the structure, the outer function, and the inner function. Then we apply steps. Differentiate the outer function, multiply by the derivative of the inner function. So the process becomes identify structure, then apply outer rule, then apply inner rule, combine the results. This is exactly like chaining inference rules in logic. So the chain rule is a perfect example of multi-step reasoning in calculus. Now let's see a practical example. Here's a classical problem. F of x equal to x square plus 1 whole raised to 3. In the first step, we apply the power rule to the outer function and we get 3 into x square plus 1 whole square. Then in the step 2, we apply the chain rule and multiply by the derivative of the inner function. And the step 3, we differentiate the inner functions x square plus 1. and the result will be 2x. In the first step, combine everything. So the final answer is f dash of x equal to 3x square plus 1 whole square into 2x. So now the important observation is each step follow a specific rule, so the entire solution is actually a sequence of rule applications, just like inference steps. Predictability of expressions. Now let's discuss why this approach is powerful. Rule-based systems in calculus have three important properties. The determinacy property, which says the same input always gives the same output. A consistency property, which says the rules do not contradict each other. And the predictability property, which results can be anticipated before solving. This is exactly how logical system behaves. So we can say calculus is not random. It is a formal system with structured rules. This makes it reliable and suitable for automation. Now let's talk about the applications. This concept has many real-world applications. The symbolic computation, in which the tools like Wolfram Mathematica apply rules automatically to computer derivatives and integrals. And then computer algebra system, which has they simplify the complex expressions using rule-based transformation. Then there's AI-based math solvers, it is used in machine learning for automatic differentiation and gradient computation. These systems rely entirely on rule matching, step-by-step transformations. So formalizing calculus as inference rules enables powerful computational tools. To conclude all this, we have seen that the calculus can be understood as a rule-based inference system. It helps to structure reasoning, ensure accuracy, enable automation. Each step in calculus is not random. It is guided by well-defined rules. So, at last, the mathematics is not just about finding answers, but about following a logical and systematic process. Thank you.